Okay, physics, we're ready for chapter 14. It's going to be on waves and sound. We're going to be covering sections 1 and 2. Section 3 is about the wave equation, and I've posted a YouTube video for you to watch on that. Okay, we're going to look at the two different kinds of waves, and a wave is energy that is moving from one place to another. So for example, energy travels through water, but water doesn't actually move from one place to the other. The two different kinds of waves that we're going to look at, one is a transverse wave, and in a transverse wave, the displacement is perpendicular to the direction of the wave motion. So here, the individual wave, or the string, is moving up and down as the person is flicking it, but the wave itself travels from their hand over here to this barrier. So the wave goes this way, but the individual particles are moving up and down. This would be much like if you're going to do a wave at a stadium. So the individual people move up and down, but the wave moves from side to side, or maybe from the top of the stand down to the bottom. And the two parts on a transverse wave, we're going to have this region at the top of maximum amplitude, and that's called a crest. And then we're going to have this region at the bottom, and this is called a trough. Now the other kind of wave that we're going to look at is a longitudinal wave. And in this case, the particles move in the same direction as the wave. So here I have a speaker. The speaker is moving side to side, and you can see the wave, the velocity or the direction of the wave, is also moving from left to right. So the particles move in the same direction as the wave. And the two pieces that we have in a longitudinal wave are going to be the regions where it's packed all together. So this is going to be where the air particles are packed together. That's a compression. And then we have the part where they're spread apart. This is a rarefaction. I could also think about this in terms of a slinky. So if I would gather up a little bit of the slinky and then let it go, that wave would then move through the slinky. This would be my compression. This other part would be the rarefaction where they're spread apart. In a water wave, I can see I have like a little cup here at the top. This cup actually goes from the top to the bottom. So it means it's moving up and down while the wave is moving this way. So in that case, it's a transverse wave. It's also a longitudinal wave because I can see this cup is moving side to side. So it's got both pieces. And parts of a wave that we're going to look at the wavelength. We've talked about wavelength before. We've also talked about period before. We have also looked at frequency. We know that frequency is a reciprocal of the period. Now our new equation is between wavelength and frequency, and the velocity or the speed of the wave is constant for one particular medium, and if I take the wavelength times the frequency, I get that constant. So if I were going to draw a wave, and then I'll draw one here that has a higher frequency. So this top wave, this would be the wavelength. And in my bottom wave, this is the wavelength. So in the top wave, this has a lower frequency, but it has a longer wavelength. And in my bottom one, I have a higher frequency, but that is a smaller wavelength. So those are inversely proportional. Okay, next we're going to do an example. So here I have a boat and it's bobbing up and down and it has a frequency of 2.3 seconds. They want me to find the frequency. So frequency is 1 divided by the period, so 1 divided by 2.3, and it gets me the frequency, and my label then would be hertz. The second part of this problem gives me the wavelength, and it asks me to find the wave speed. So I'm going to use my new equation, which is velocity is frequency times wavelength. I'm going to plug in the frequency that I just found in the first part, multiply by the wavelength, and I'm going to get a speed of 3.7 meters per second. Now, the speed that we get is determined by the individual medium. And if we look at a string, that's going to be determined by the tension in the string, And the tension in our equation that we're going to see later is F. But if we think about it from what we had earlier, that would be F of t when we talked about tension before. In our equation, we're just going to see it F. But if we have a higher tension, we're going to have a faster speed. That means they're going to be proportional. So speed is proportional to the tension. The other factor is the mass of the string. The more mass the string has, the more inertia it has, and that means it's going to move slower. So in that case, mass is inversely proportional to the speed. So we're going to use those two factors and come up with an equation. So here we see that velocity is proportional to the tension, and the velocity is inversely proportional to the mass. And this mu is called the mass per length. And it's just what it says it is. I take the mass divided by the length. Okay, we're going to do an example. So in this case, I have a wire, gives me the mass, and it gives me the time for the wave pulse to travel. So that would be my period. So I'm first going to take and find my mass per length. So I change this grams into kilograms, divide by my length, and that is going to get me my mass per length, which would be kilograms per meter. This is the equation that I'm going to use in order for me to find the tension. But for me to find the tension, I'm going to need the velocity and the mass per length. So I need to find my velocity. Now, old equation, velocity is distance divided by time. So I take my distance, the 5.7, divide by my time. That gets my speed. So I'm going to plug that in for the velocity in the equation. And I'm going to plug my mass per unit length in the equation. To solve this, I'd have to square both sides. So I'd square this number. Squaring this side gets rid of the square root. And then I multiply by this number, and I got a force of 65 newtons. Okay, now we're going to take a look at reflection. So when a wave hits a barrier, it's reflected. If it's a fixed end, notice when this is a crest, it hits the fixed end, it comes back as a trough. So when it hits a fixed end, the wave becomes inverted. If I have a free end, then the opposite happens. Comes in as a crest, this end is free because it can slide over here on this rod. It comes back as a crest. So it comes back on the same side instead of being inverted. And that's all that we're going to look at in this PowerPoint.